Dear students, today I am going to talk about the complex number, complex variable, and the analyticity. So let me start with the definition of complex variable or complex number. A variable of the form z equal to x plus iy, where x and y both are both are real numbers, is called a complex variable. It's called a complex variable. So if I say that x and y are two real numbers, and if I write z equal to x plus iota into y, then the total thing is called complex number or complex variable. Now let me define complex function. Let me define complex function. So a function omega, which is nothing but function of z. Z is function of xy, but here w or f is a function of z, which is written as u of xy plus I v of xy, or simply you can write as u plus iv is called a complex function. Is called a complex function. So here you see that if z is a complex variable, then the function of z is called complex function. Here, in case of z, x is the real part, y is the imaginary part. In the case of w or f of z, we can have u plus iv, where u we will call as a real part, v we will call as a imaginary part. Remember that they are not constant, they both are functions of x and y. For example, say we will consider w equal to z square. W equal to z square. Z square means here w we say it is f of z, function of z, and that is equal to z square. So what is the real part? What is the imaginary part? How can we find the real and imaginary part? That is u and v. We can write here z equal to x plus iy, we know. So square of that one. Square of that one is equal to x square plus iy square. A square plus a plus b whole square formula I am putting, plus 2 into x into iy. So if we rewrite it, what we will get? X square, I square is minus 1, y square, so minus y square plus I into 2 into xy. So here you see that this is equivalent to saying u plus iv. So what will be my u? U will be real part of this expression. The real part is x square minus y square. X square minus y square. And v will be the imaginary part, which is nothing but 2xy. 2xy. So like that, we can able to find the real and imaginary part for a function w omega or f of z. Now, if it is a simple function y equal to f of x, we can have a continuity, differentiability, all those things. Similarly, for the complex function also, we can have continuity, differentiability. Okay, so to define analyticity, we need the continuity as well as differentiability of the function. So let me give you the definition of continuity of a complex function. Continuity of f of z. Under which condition a function f of z is continuous. So just recall the continuity definition for the real value function y equal to f of x. In the similar way, in place of real variable x, we are having here complex variable z. So under which condition we will say f of z is continuous is a complex function f of z is said to be continuous at z equal to z naught. Z equal to z naught is a particular point at z equal to z naught if if limit z tends to z naught, f of z should be equal to the value of the function f at z naught. So it is similar to the definition of real valued function. If limit z tends to z0, f of z is equal to f of z0, then we say the function is continuous. Limit of the function at z0 is equal to value of the function at z0. Now let me give you the differentiability of the function. Now differentiability of f of z. Okay, differentiability means under which condition the derivative exists. A complex function, a complex function f of z is said to be differentiable at z equal to z naught if z equal to z naught in a domain D if limit delta z tends to 0, f of z0 plus delta z minus f of z0 divided by delta z, provided this limit exists. If this limit exists, we denote it by f dash of z0. We denote it by f dash of z0. So this is the definition for the differentiability of a complex function f of z. Delta z is small change in z. If this limit exists, then we will denote it f dash of z0 and we say that the function is differentiability. Now based on the continuity and differentiability, I will define analyticity of the complex function. Now analytic function. Analytic function. Under which condition the function f of z is analytic. So first I will give you the standard definition of analytic function. Then we can go for the alternative method to check the analyticity using some other theorem. So now what is actual definition of the analytic function is a complex function a complex function f of z defined in a domain D is said to be analytic at a point z naught in the domain D if it is not only differentiable at z naught but also in some neighborhood of z naught. That means here you see differentiability we are checking at z naught. So limit delta z tends to 0, f of z0 plus delta z minus f of z0 divided by delta z means we are defining the differentiability at z naught. So analytic, the function f of z will be analytic if it is only not only differentiable at z naught but in the some neighborhood of the z naught. That means if I have a point here z naught, then it will be differentiable around the point z naught. These are the neighborhood of the point z naught. So then I say the function is analytic at the point z0. So it is non-local. It is non-local. Now this is exact definition thing. Now to solve the to check whether the function is analytic or not analytic, always using this one may be difficult for you. So I will give you one theorem stated by Kusi-Riemann that will give you easily whether the function is analytic or not. And that theorem is like this: necessary and sufficient condition of and sufficient condition to be analyticity or analytic function. Analytic function. Actually, there are two statements. One will be for necessary condition and other one is for sufficient condition. But I am combining both of them and I am giving it one place and I am saying that necessary and sufficient condition to be an analytic function. So what I will do is the function f of z, which is nothing but u plus iv, or you can stay to it. Okay, so the function f of z u plus iv is said to be analytic, or you can say the necessary and sufficient condition, the necessary and sufficient condition for the function to be analytic is that is that what is the thing? ux uy, that means partial derivative of u, partial derivative of v with respect to both x and y. Ux means partial derivative of u with respect to x, partial derivative of v with u with respect to y, and similarly vx and vy all exist. They should exist, are continuous. They should exist and they should be continuous and satisfies the Cauchy-Riemann equation. Cauchy-Riemann, in short form you can say CR equation. Cauchy-Riemann equation. As what is the Cauchy-Riemann equation? The Cauchy-Riemann equation is ux should be vy. The partial derivative of u with respect to x should be partial derivative of v with respect to y. And partial derivative of u with respect to y should be equal to negative of partial derivative of x with respect to x. So these two equations are called CR equation. These two equations are called CR equation. So alternatively, to check the analyticity of a function, we can apply the CR equation provided the derivative exists and they are continuous. If any one of the derivative are not continuous, then we cannot say we cannot go for the CR equation. So if this thing happen, then we can say the function is analytic. For example, simply I will take an example here. Simple example, say I will write test for the analyticity. Test for the analyticity. Analyticity of f of z of f of z equal to z conjugate. So whether this function is analytic or not, we have to take. Of course, the exact definition we can apply, but for that we have to check whether it is differentiable or not, or and continuous or not. That we have to check. But we can check it easily using the CR equation. In order to use the CR equation, first I will identify what is the u and what is the v. So here we know z. We know z is nothing but x plus iy. So z conjugate will be x minus iy. But z conjugate is nothing but f of z. And f of z is nothing but u plus iv. So here in the z conjugate, whatever real part is there, we will consider it is as u. And whatever imaginary part is there, we will consider it as v. So now here what is my u? U is nothing but x. And what is our v? V is nothing but minus y. Now whether it is satisfying the CR equation or not, we will check. So let me find ux. Derivative of u with respect to x is 1. Then I will find uy. Derivative of u with respect to x. Y is 0. Similarly, I will find Vx, derivative of v with respect to x is 0, and Vy, derivative of v with respect to y is minus 1. Now according to the CR equation, ux should be equal to Vy. So what is my ux? Ux is 1. What is my Vy? So ux should be equal to Vy. But ux is 1 and Vy is minus 1. Whether they are equal? So they are not equal. So I can say that ux is not equal to Vy. So any one of the condition is not satisfied, then we cannot say that it is analytic. To be analytic, both the condition should be satisfied. So one condition it is not satisfying, so there is no need to go for any other condition. Therefore, we can say that it is not analytic. Therefore, f of z equal to z conjugate is not analytic. not analytic, everywhere, everywhere. Similarly, we will take another example here. Say I will check test for the analyticity of of f of z equal to z square. F of z equal to z square. Here, you know z is nothing but we know z equal to x plus iy. Then we can find z square. Z square means x plus iy whole square, and that will be nothing but by the formula of a plus b whole square. We can have here x square plus iy square plus 2 into x into iy, and finally we will get here x square minus y square plus I into 2x y. So here, this is my f of z. F of z is nothing but u plus ib. But u plus ib is nothing but x square minus y square plus I into 2xy. So now you compare the real and imaginary part. So real part here is u. Real part here is x square minus y square. So you take u equal to x square minus y square. And imaginary part here is v. Imaginary part here is 2xy. So you can take v equal to 2xy. Now you find ux. You find ux. Ux is derivative of u with respect to x, which is 2x. And then find uy. Derivative of u with respect to y is minus 2y. Similarly, you find vx. Vx derivative of v with respect to x is 2y. And find vy. Derivative of v with respect to y is 2x. Now you see that by the CR equation, whether ux is equal to vy. So ux is how much? 2x. And vy is how much? Again 2x. So first condition is satisfied. Then I will go to the second condition. Uy equal to minus bx. Equal to minus bx. So uy is how much? Uy is minus 2y is equal to minus of vx. Vx is 2y, so minus 2y. So minus 2y equal to minus 2y. So uy is equal to vx also satisfied. Therefore, f of z is z square is analytic analytic everywhere. Analytic everywhere. Say I will take another example here. I will take another example. Suppose I will take f of z equal to mod z square. Whether it is analytic or not. Whether it is analytic or not. So for that we have to find the real as well as imaginary part. For that we need to find real and imaginary part. So here f of z means u plus iv, but that is nothing but mod z square. Z is nothing but x plus iy mod square. So you know that mod of a complex number is nothing but mod of a complex number with nothing but root over of root over of the sum of square of the real number, but here square is there, we will take square. So finally what we will get? X square plus y square, and there is no imaginary part. There is no imaginary part. And so what is my u? U will be x square plus y square, and v will be 0. There is no imaginary part. And so we can have ux equal to 2x, uy equal to 2y, and vx equal to 0, vy equal to 0. So we can see that in the normal way ux is not equal to vy and uy is not equal to minus bx. So therefore it is not analytic. Therefore it is not analytic. It is not analytic. But you see that if I put x and y both are 0, then 2 into 0 will be 0, 2 into 0 will be 0. So they will be equal to, ux will be equal to vy and uy will be equal to minus bx. So therefore, whenever you are getting f of z equal to z square, you can say that it is not analytic everywhere except z equal to 0. Therefore, f of z is mod z square is not analytic everywhere except z equal to 0. So it is z equal to 0 means x plus iy equal to 0, and under which condition it will be 0? If x equal to 0 and y equal to 0, then z will be 0. So z equal to 0 is equivalent to saying x equal to 0, y equal to 0. So if this f of z equal to mod z square is analytic only at z equal to 0 and nowhere else. Nowhere else. Suppose I will take another example here. Suppose I will take another example here. F of z is equal to sin z. F of z equal to sin z, whether it is analytic or not. So we know that z equal to, z equal to x plus iy. And now we have to find the real and imaginary part for sin z. So we have f of z, which is nothing but u plus iv, and sin of z means I can say x plus iy. So you know the formula of sin of a plus b. Sin of a plus b is sin a cos b plus cos A sin B. Now here A is x, B is Iy. And so this one will be equal to sin of x into cos of Iy plus sin of Iy into cos of x. So you remember that cos of iy or sin of iy means they are belonging to hyperbolic function. So sin x will be as it is, cos iy will be hyperbolic cos y, cos hyperbolic y, and sin of iy will be I into sin hyperbolic y into cos x. Now you compare the real and imaginary part. So then we will get u will be nothing but sin x cos hyperbolic y, and b will be nothing but sin hyperbolic y cos x. Now whether it is analytic or not, for that we will go for CR equation. CR equation means we have to find the derivative of u with respect to x. The derivative of u with respect to x will be nothing but derivative of sin x cos hyperbolic y will be constant with respect to x. Derivative of sin will be cos, so cos x cos hyperbolic y. Similarly, uy, derivative of u with respect to y. Remember, whether it is cos or sine, derivative of hyperbolic function is always positive. If it is cos y, I could have written derivative of cos y is minus sine y. But here cos hyperbolic y is there, so I will write here sin x will be as it is, and that will be sine hyperbolic y. That will be sine hyperbolic y. Similarly, if I go for vx, derivative of b with respect to x, derivative of cos, it is not hyperbolic, so derivative of cos will be sine. So I can write here minus sin x sine hyperbolic y. And Vy, derivative of v with respect to y sine hyperbolic y, that will be cos hyperbolic y into cos x. Now you see that here ux is cos x cos hyperbolic y will be equal to vy. Vy is cos x cos hyperbolic y, and you see that uy will be uy sin x sin hyperbolic y, and v minus, that will be here uy equal to sin x sin hyperbolic y, that equal to minus of minus sin x sin hyperbolic y. So minus of minus will be plus, but this one is nothing but this is equal to minus bx. So uy equal to minus bx. Uy equal to minus bx. So both the shear conditions are satisfied. Therefore, we can say it is analytic everywhere. Therefore, f of z equal to sin z is analytic everywhere. Everywhere. Now another problem I will do here. Take the analyticity of, say, I will write f of z equal to e to the power x into cos y plus I sin y. Okay. So whether this function is analytic or not. So in order to use the CR equation, we have to find the real as well as imaginary part. So let us find the real and imaginary part. F of z equal to u plus iv. But here f of z equal to e to the power x cos y plus I into e to the power x sin y. Sin y. Now if you compare the real and imaginary part, u will be nothing but e to the power x into cos y, and v will be nothing but e to the power x sin y. Okay, so now find ux, derivative of u with respect to x. When we are finding derivative of u with respect to x, cos y will be constant. Derivative of e to the power x will be e to the power x cos y. Then uy, when we are finding derivative of u with respect to y, e to the power x will be constant. Derivative of cos y is minus sin y. So e to the power x sin y minus of that. Similarly, we will find Vx. Derivative of v with respect to x will be e to the power x as it is sin y. And Vy is nothing but e to the power x will be constant with respect to y. Derivative sign will be cos. So e to the power x cos y. Now you can see that ux will be equal to Vy. Ux is e to the power x cos y, Vy is e to the power x cos y. So first condition is satisfied. Similarly, we will go for second one. Uy is equal to minus e to the power x sin y. But e to the power x sin y is nothing but Vx. And so that will be minus Bx. So Uy equal to minus Bx. So both the conditions are satisfied. So we can say that this function f of z e to the power x cos y plus I sin y is analytic. Analytic everywhere. Everywhere. Now, this is the procedure we follow in the case of Cartesian coordinate. Already I gave you example f of z equal to z, z square and zq. So up to that we can find the formula of z. Z will be x plus iy whole square or z square, and zq will be x plus iy to the power 3, and we can able to expand it and we can able to find the real and imaginary part. But what will happen? Say I will ask you, check whether f of z equal to z to the power 7 is analytic. Is analytic. So how can we check that one whether it is analytic or not? We cannot. It will be time taking. If we expand that one, z to the power 7 means we will write x plus iy to the power 7. So it is very difficult for us to expand this one and find the real and imaginary part. In that case, what we will do is we will try to represent the complex variable z by a polar coordinate. Hence, I would like to give you how to the representation of a complex variable by a polar coordinate. So, representation of z, which is x plus iy by polar coordinate. By polar coordinates. So how can we write it is, let x equal to r cos theta and y equal to r sin theta. So if I put x equal to r cos theta, y equal to r sin theta in z, what we will get? Z will be nothing but r cos theta plus I into r sin theta. And here we can get r is common, so cos theta plus I sin theta. But cos theta plus I sin theta is nothing but e to the power I theta. So r into e to the power I theta. R into e to the power I theta. So the polar representation of the complex number z is nothing but r e to the power I theta. So what is generally r? The r is nothing but, where r is nothing but, if I have z equal to x plus iy, then r will be nothing but root over of x square plus y square, and theta will be nothing but tan inverse of y by x. Tan inverse of y by x. In that case, in this case, how can we check whether it is analytic or not? For that, the CR equation, the CR equation in polar form. The CR equation in polar form will be given as, find the derivative of u with respect to r, and that will be equal to 1 by r into b theta. This is the first equation. And second one will be, find the derivative of v with respect to r, and that should be equal to minus 1 by r u theta. So this is the CR equation. This is the CR equation in the case of polar form. In the case of polar form. Now simple example I will take, whether say I will write here, I will take here, check whether the function f of z is z to the power n is analytic. Is analytic or not. So how can we check? If I write z equal to x plus iy, it will be very difficult for me to expand a x plus iy to the power n and to find the real and imaginary part. So what I will do is, I will try to convert this one to the polar form. So z equal to, already I gave here, z equal to r into e to the power I theta. So here I can write the polar form as f of z polar form will be r e to the power I theta to the power n. And so that will give you r to the power n e to the power I n theta. e to the power I n theta, and this will be nothing but r to the power n e to the power I n theta is equivalent to cos n theta plus I sin n theta. Okay, so from here we can find Rn cos n theta plus I into Rn sin n theta. So this will be equal to u plus I v, u plus I v. So what is my u? U will be nothing but r to the power n cos n theta, and my v will be nothing but r to the power n sin n theta. Now you find ur. Ur means derivative of u with respect to r. So by that time cos n theta will be constant. Derivative r to the power n is n into r to the power n minus 1 cos n theta. Now find u theta. U theta means derivative of u with respect to theta. So derivative of cos is minus sine, and so I will have n minus of n r to the power n will be as it is sine n theta. Okay. Similarly, we will find VR. VR will be nothing but derivative of V with respect to R and R to the power n minus 1 sine n theta. And V of theta is nothing but R to the power n will be as it is. Derivative of sine n theta is n into cos n theta. Now you see that UR UR is equal to n into r to the power n divided by r, because minus 1 is there, into cos theta, and so we can write 1 by r into n r to the power n cos n theta, cos n theta. But n into r to the power n cos n theta is nothing but how much? V theta. B theta. So we are getting here u are equal to 1 by r b theta. So first condition is satisfied. The polar form of u are equal to 1 by r b theta. Now whether the second condition is satisfying or not. What is the second condition? U r is minus n r to the power n sin n theta, and this is, we want to show that this is equal to 1 by v theta, v are equal to 1 by r. So this I can write in this way. This implies minus n into r to the power n minus 1, r to the power n minus 1 into r sin n theta, sin n theta. And I can say that that will be equal to this minus r minus, and r I will take that side. So this may give you minus 1 by r ur will be nothing but n r to the power n minus 1 sin n theta. But r n to the power n minus 1 sin n theta is nothing but vr. So I can say here vr. So from there you will see that vr equal to minus 1 by r u theta. So this is my u theta. This is my u theta. Okay. So this is the procedure to check the analyticity of a function using the necessary and sufficient condition or CR equation. Thank you.